Hello. Let's look at these exercises now. Now that you've tried them yourself, check your answers here. As always, feel free to skip ahead to a few minutes in so you can actually see the answers. But if you're stuck, feel free to watch my whole explanation as well. All right, so how much algae is there initially? So initially means after 0 days. So that means after t equals 0. And you can get that by doing 20 times 2 to the power 0. And 2 to the power 0 is just 1, so that gives you 20 times 1, which is 20. So that means there's 20 grams initially. Okay, after 1 day, that means t equals 1, and that's going to be 20 times 2 to the power 1. So 2 to the power 1 is just 2. This gives you 20 times 2, which is 40 grams after 1 day. What about after 5 days? So that's going to be when t equals 5. And we're going to get 20 times 2 to the power 5, which really just means 20 times 2 times 2 times 2 times 2 times 2. So 20 times 2 is 40. 40 times 2 is 80. Times another 2 is 160. 160 times 2 is 320. 320 times 2 is 640. So there's 640 grams after 5 days. Okay, so what does the 20 and the 2 tell you about the algae? Well, the 20, that's what we got as our initial value. So 20 grams is the initial amount of algae in the pond. And what does the 2 tell you? Well, every time 1 day goes by, the exponent is going to go up by 1, which is another multiplication by 2 that happens. So the 2 means that every day the amount gets multiplied by 2. Okay, now let's look at exercise 2. So we're given that at some point an aquatic herbicide, so like plant poison you put in water, is introduced into the pond to try to kill some algae, and the algae begins to clear. So the number of grams of algae remaining t days after the introduction of the herbicide is given by 8,000 times 1/2 to the power t. So if you fill in this table, you should be getting 8,000 here because it's times 1/2 to the power 0. That's the initial value. When t is 1, you're going to do 8,000 times 1/2 to the power 1, which is just times 1/2. That's going to be 4,000. And the next one here is going to be 8,000 times 1/2 to the power 2. So that's times 1/2 times 1/2. It's the same as this one, it's just getting multiplied by another 1/2. So that's going to become 2,000. Here, we're doing 8,000 times 1/2 to the power 3, which is just like 8,000 times 1/2 to the power 2, but multiplied by another factor of 1/2. So 2,000 times 1/2 is 1,000. And you could, of course, also just get that by working this whole expression out. You should get 1,000. Okay, so part B says if the amount of algae was described by 8,000 times 1/5 to the power t, what would be different? Well, let's see. Here it's getting multiplied by 1/2. So every day there's half of the amount of algae that there was before. If it was getting multiplied by 1/5, you'd have 1/5 of the amount of algae that there was before. So I just wrote that out here. Now, what would that mean in terms of numbers? It means it would be decreasing faster. It would be going from 8,000 at the start when t is 0. Make a little mini table here. And then after 1 day, 1/5 of 8,000 would be, I'm having a brain fart. What's 1/5 of 8,000? Would be 1,600. And after 2 days, there would be 1/5 of that remaining, which would be 320, I think. Yeah, 320. I just had to pause the recording to check that on my calculator. Hopefully you're pausing the recording every once in a while too to check things yourself, because it does go kind of fast sometimes. So yeah, it's decreasing a lot faster than it was when the growth factor is 1/2. Okay, so let's try to now model some situations with an exponential function. So first we have the number of animals, n, in a population is initially 880, and the size of the population increases by a factor of 1.14 every year. So this is giving you the initial value. That's like the A in the formula, and it's increasing by a factor of 1.14 every year. That's describing the growth factor, B. Is 1.14. So if we're saying that n equals a times b to the t, that's going to be n equals 880 multiplied by 1.14 to the power t. So that is an exponential function that describes the situation. You can check if you want to plug in t equals 0, should give you a result of 880. That's the initial population. Then, every time t increases by 1, you're multiplying by 1.14 again. So, all right, let's look at B. When a food source runs out, the number of bacteria in a petri dish starts at 20,000 and then decreases by a factor of 0.4 every day. So just to give you an idea what this looks like, I'll show you a table. So starting at 20,000 when t equals 0, every time 1 day goes by, it gets multiplied by 0.4 again. So 20,000 times 0.4 is 8,000. 8,000 times 0.4 is 3,200. That times 0.4 is 1,280. So the fact that this is 0.4 means it's going down. So you could call, instead of calling that a growth factor of 0.4, you might call it a decay factor. But in any case, the formula for this is going to be B equals 20,000 times 0.4 to the power t. And it doesn't matter what you call the b and the t, any variable you want to use means the same thing. So you can call it y equals 20,000 times 0.4 to the power x, or whatever you want. And the parentheses here are kind of optional too. They're just sort of emphasizing that you're talking about multiplication here. If you just want to write it with the dot, that's okay too. Okay, I'll do the next exercise in the next video. Exercise 4 is an important kind of practice to get. It's something you should definitely be able to do, especially because you can use a calculator to help you with the arithmetic if you need it. But the more you do by hand here, this is really good practice, the better off you'll be. And I'll show you those answers in the next video.